Hello students, we will continue with chapter 4 problems and solutions part 4. A uniform magnetic field of 3000 Gauss is established along the positive z direction. A rectangular loop of sides 10 cm and 5 cm carries a current of 12 ampere. What is the torque on the loop in the different cases shown in the figure? What is the force on each case? Which case corresponds to stable equilibrium? So we have a uniform magnetic field for all the diagrams. We have B acting in the upward direction along the z-axis, and the value of B is 3000 Gauss. Now 3000 Gauss we have to convert it into Tesla. So 1 Gauss is 10 to the power minus 4 Tesla. So 3000 Gauss will be 3000 into 10 to the power minus 4. So you will get it as 0.3 Tesla. We can see the rectangular loop in different positions in the diagrams. So we consider anti-clockwise as positive and clockwise as negative. We have to find out the torque on the loop in all the different cases and also the force in each case, and we have to find which of these cases correspond to stable equilibrium. So the data is given there. Magnetic field strength B equal to 3000 G, and when you convert it into Tesla, you get it as 0.3 Tesla. The length and breadth of the loop is given as 10 centimeter and 5 centimeter. So the area of the loop is important here to find torque. So we have to multiply length into breadth and convert it into meters squared. So you get 50 into 10 to the power minus 4 meters squared as the area of the loop. Then current in the loop is 12 ampere, and as I mentioned, anti-clockwise is taken as positive. The formula for torque 2 vector is equal to Ia vector cross B vector. And the expansion or magnitude of torque will be IAB cos theta. Sorry, IAB sin theta. Cross product is sin theta. Okay, let us take the first two cases. A and B, they are similar. So here we have B in the upward direction, that is Z, and this is the rectangular loop carrying current in the anti-clockwise direction, and we have the area of the loop facing towards the positive x-axis. Now the formula for torque is Ia vector cross B vector, and the formula for force is IL vector cross B vector. L will be the length of the loop. So you have the angle between them to be, so look at this. Torque is equal to I. 12 is I, and area is 50 into 10 to the power minus 4, and the direction along the x-axis is given as I vector, unit vector I, cross 0.3 is B, and we have the direction along K vector. So I cross K, you know, is minus J vector. So you get your answer in minus J vector, which means J stands for y-axis. So the torque direction will be along the negative y-axis. So we get torque to be 1.8 into 10 to the power minus 2 Newton meter, and the direction of the torque is negative y direction. The force on the loop is 0 because angle between L and B is 0. Here, this will be the length. So the angle between the length of the loop and the magnetic field will be 0 because they are both in the same direction. So we have force will be equal to 0. Sin 0 is 0. Now the second case B is also exactly similar to the case A. Now look at the case C. Here we have the area pointing to the positive y-axis. The direction of area it is facing the positive y-axis, and B is like before in the z direction. So when you multiply vectorially, torque vector is equal to 12 into, that is IA vector. Now area is along the y-axis, so we have to use J cross. B is along the K vector, is along the z-axis, so it is cross K. And J cross K will be minus I. That means you get torque to be 1.8 into 10 to the power minus 2 Newton meter along the negative x-axis. Negative x-axis, and force is 0 because the angle between B and L is 0. So let us look at the next case, that is case D. Here we have the area, the coil at an angle 30 degrees to x-axis. You can see it here. So area, the direction of area will be perpendicular. It is normal, perpendicular. So there's a total of 90 plus 30 degrees. 90 plus 30 degrees here. So we are going to find only the magnitude of the torque. So the magnitude of the torque is given as IAB. So 12 into 50 into 10 to the power minus 4 into 0.3. You get 1.8 into 10 to the power minus 2 Newton meter. And the torque direction will be at an angle of 240 degrees with positive x direction. So that will give you 360 minus 90 plus 30, that is 120, which is 240. And the force is 0. So force is IL vector cross B vector. Now the next case, E. Here we have the coil in this position, and the direction of area of the coil is same as the direction of B. Both are in the same direction, Z axis. So when you calculate torque, you get 50 into 10 to the power minus 4 into 12 K. Both are in the same direction, so K cross K is 0. So here torque is 0 and the force is also 0, and therefore this is a case of stable equilibrium. A and B are in the same direction. So here the equilibrium is stable. Now the last case, we have area. The current is reversed. So area points downwards and B is upwards. So there is an angle of 180 degrees between A and B. But one is along the positive z-axis and the other one is along the negative z-axis. So we have K cross K again, which is equal to 0. Here the torque is 0 and the force is also 0, because you know sine 180 is 0, and this is unstable equilibrium because when this is disturbed, it will not come back to its original position. So here the equilibrium is unstable. Next question. A circular coil of 20 turns and radius 10 centimeter is placed in a uniform magnetic field of 0.10 Tesla normal to the plane of the coil. If the current in the coil is 5 ampere, what is the total torque on the coil, total force on the coil, and average force on each electron in the coil due to the magnetic field? The coil is made of copper wire of cross-sectional area 10 to the power minus 5 meters squared, and the free electron density in copper is given to be about 10 to the power 29 per meter cubed. So let us look at the question. There is a circular coil. There are 20 turns. Its radius is 10 centimeter and placed in a uniform magnetic field of 0.1 Tesla normal to the plane of the coil. Normal means perpendicular to the plane of the coil at an angle 90 degrees. So the current in the coil is given as 5 ampere. So what is the formula for total torque on the coil? So you know the total torque on the coil is given by NBIA cos 90. And cos 90 we have as 0. So we get the total torque as 0. And net force is also 0 because the net force on a current carrying loop in a uniform magnetic field is always 0. Now the third part, what is the average force on each electron? So we have the magnetic force. There will be a force. Electron is a charged particle and it is moving in a magnetic field B. So the magnetic force or Lorentz force acting on each electron is given by B into E into V. E is the charge of the electron and Vd is the drift velocity of the electron. Now we already know drift velocity has a formula I by NEA. The number of electrons, charge of an electron, and the area of cross section of the wire. So we substitute all these values and you get force to be 5 into 10 to the power minus 25 Newton. So the average force on each electron is 5 into 10 to the power minus 25 Newton. Next question. A solenoid 60 centimeter long and of radius 4 centimeter has 3 layers of windings of 300 turns each. A 2 centimeter long wire of mass 2.5 gram lies inside the solenoid near its center normal to its axis. Both the wire and the axis of the solenoid are in the horizontal plane. The wire is connected through 2 leads parallel to the axis of the solenoid to an external battery which supplies a current of 6 ampere in the wire. What value of current with appropriate sense of circulation in the windings of the solenoid can support the weight of the wire? Given G equal to 9.8 meter per second squared. So here we have a solenoid. It has a length 60 centimeter and radius 4 centimeter with 3 into 300, that is 900 turns. And there is a long wire lying inside the solenoid perpendicular to its axis. Both the wire and the axis of the solenoid are in the horizontal plane, that means in the plane of the paper. Now the wire is connected through 2 leads parallel to the axis of the solenoid to an external battery which supplies a current of 6 ampere in the wire. So what value of current in the windings can support the weight of the wire? The wire should not fall down, it should be supported by the magnetic force. So what current should we supply so that we can produce a magnetic force which will support the weight of the wire? So let us see the formula for magnetic field. B equal to mu naught Ni by L. And magnetic force is given by F equal to BIL. So we get F equal to mu naught Ni by L into I into L. Now the force on the wire, that is the magnetic force created, should be equal to the weight of the wire. So that should be equal to mg. And from this we can deduce I equal to mgl by mu naught NIL. So substitute all the values from the given data and you get your answer to be 108 ampere. Next question. A galvanometer coil has a resistance of 12 ohm and the meter shows full scale deflection for a current of 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volts? So a galvanometer coil, you are going to convert a galvanometer into a voltmeter. And as you know, the theory, to convert a galvanometer into a voltmeter, you need to connect a high resistance in series with the galvanometer. So we are going to find out what is the high resistance needed. So the formula is V by Ig minus G. V is the range which we need for the voltmeter. Ig is the milliampere current that is flowing. and capital G is the resistance of the galvanometer coil. So you have to work the first part, V by Ig first, get an answer and then subtract 12 and you will get your answer to be 5988 ohms. Now the next question, a galvanometer coil has a resistance of 15 ohms and the meter shows full scale deflection for a current of 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 ampere? So here we have the conversion of a galvanometer into an ammeter. And you know the theory, to convert a galvanometer into an ammeter, we have to connect a very low resistance called shunt resistance in parallel with the galvanometer. And the formula for that shunt resistance is given by S equal to Ig into G by I minus Ig. Here Ig is the milliampere current that flows through the galvanometer. I is the range of ammeter that we require, and when you finish your calculations you will get 0.01 ohms or 10 milliohms. That's a very small value of resistance, and when it is connected in parallel with the galvanometer will function as an ammeter. Thank you, students. That's all for today.